Good morning, everyone. I'm very happy to present Jana Zinkernagel from Geisenheim University. Jana will talk about crop-specific water balance of vegetables, opportunities and constraints arising from the Geisenheim Irrigation Scheduling. Jana, the floor is yours.
Thank you very much, Ofer. It's really a pleasure and an honor to be here at your seminar. And within the next about 45 minutes, I would just show you some insights about our experiences on a scientifically based, but also on a practical point of view about the use and the usability of crop-specific water balance of vegetable crops under Central European conditions, considering the climate, the temperate climate, but also considering the structure of vegetable farms being characterized by small-scale farmers, plots and fields having a huge variety of open field crops. And I think maybe this might be somehow different to Israeli conditions. So after my talk, I would be very interested in having a discussion with you and to compare your knowledge, your conditions with ours. So therefore, I chose the title Opportunities and Constraints Arising from the Decision Support System, Geisenheim Irrigation Scheduling as a tool for irrigation in Europe. So as I knew, you are agricultural meteorologist, hydrologist, soil physics, so you're very or you have a huge variety of knowledge. And Ofer told me that you're focused in irrigation, water management, but also soil erosion, treated wastewater, and agricultural waste. So I tried to meet your interests within my seminar. To evaluate our crop-specific climate water balance, I'll choose to mirror the evolution of the Geisenheim irrigation scheduling, and I will focus on the parameterization and how we evaluate KC values in Geisenheim, and I will really focus on the different approaches, and I want to evaluate those for predicting KC values. I will show you what are our current future model approaches here in Geisenheim. And at the end, I will show you our experience we gained in irrigation scheduling and also developing irrigation techniques for semi-arid conditions in our project in North Namibia. So my focus will be the evaluation of the KC estimations via phenological stages. The second approach is the KC estimation via stage duration. And the third approach I would like to discuss with you is the temperature sum model-based prediction of changes of KC values. So the first, the KC estimation via phenological stages provides the basis of the classical DSS, which have been developed in the last centuries, about 30 years. So, and this is, as you can see, the evolution I would like to share within my talk. So I'd like to start with the principle of the Geisenheim irrigation scheduling. It's a very simple approach. It's a single KC approach, really relying on the efforts and the requirements of German farmers. The ETC, the crop-specific evapotranspiration, is calculated by the product of ETO, which is the ETO FAO 56 Payment-Monteith equation, which derived as the most useful and most universally applicable under also the varying conditions in Germany. And the KC values are derived experimentally. I will show you immediately, but I think the specificity of our KC values is that the experimentally determined KC values are assigned to phenological stages of the crops. So as you can see here for onion, we have 4 stages. The first stage is characterized by the germination, and it's called after emergence. The second KC stage is 5-leaf stage, 8 leaves, and then when the leaves bend, we stop irrigation, and therefore we choose the KC4 as non-irrigated, so KC0. The calculation of the climate water balance in the GS includes irrigation thresholds, which are crop specific and soil specific, and the irrigation thresholds account for the rooting depth during or in course of the crop growth. So in respect of the water holding capacity in the rooted soil, we choose different irrigation thresholds. In this example, we have the irrigation threshold of 10, 20, and 30 millimeters. I think something relevant to know for you, in Germany, the most widely applied irrigation technique is sprinkler technology. So therefore, also the technology involves higher volumes of single water supply events. And maybe also something different to Israeli condition is that also due to the high requirements of vegetables, and also considering the non-limited water supply, there's still limited water supply under several conditions, the target soil moisture is 60 to 90% of field capacity. So how are our KC values parameterized? We follow 2 steps. In the first step, we experience the actual evapotranspiration and wiring lysimeter, as shown here for parcels. So the containers are weighed on a daily basis, and the KC values are derived from the quotient, which is formed from the measured crop evapotranspiration and related to the reference evapotranspiration. So what you can see here is the course of the KC values in those lysimeters for parcel. It's a moving average, which you can see here. So you see that in correspondence to the climate conditions, plant growth is involved, and therefore the crop evapotranspiration has a specific course due to plant growth, but also due to the daily climate variables. The KC values represent a mean value of a defined developmental stage, which is easy to be recognized by the user, and it's, which is very characteristic for this crop stage, and therefore also represents the crop specific or the stage specific water demand. These stages, for example, here in the first step, derived from the lysimeter, accounts for .4, 1.1, and 1.5 at the end of the parcel crop. Since we know that this is an artificial condition, and maybe the ETC might be overestimated related to practical conditions, we run open field trials at least 1 to 3 years, and we differentiate those KC values. And as you can see, we usually reduce the KC values derived from the lysimeter to account for the appropriate water demand under field conditions. Also, a specificity in Geisenheim that those KC values finally are evaluated after parameterization, evaluated based on marketable yield and quality. So the main target is not water shortage or to increase water use efficiency, like other approaches are targeted on. But really, the Geisenheim irrigation scheduling is focused on rather non-limited water conditions and the best yield and quality we can obtain with irrigation scheduling. By doing so, within the last 30 years, we evaluated KC values for around 25 vegetable crops, which are available for everyone, companies, farmers, or even companies for supporting decision support systems, including our approach, our models. So to evaluate that approach, I think a con is that the farmers, even if it's very simple to recognize those phenological stages, if farmers or users miss to select the appropriate KC stage, this water balancing might be distorted. So, and also the balance won't be fit to the actual water demand of the crop. The on-site recording is time consuming, considering that farms have usually 10 to 20 different plots for single crops. So it's very labor consuming. And if the labor is not really skilled, it might be error prone. And I think from the scientific point of view, we think that the dynamic of the KC changes are really poorly displayed by the stage model as shown for the parcel course. So if you just focus on that figure, you see always at the early beginning of the stage, we overestimate the evaporative demand. At the end of the KC stage, we underestimate the water demand. So this is something we have to overcome, or we did also overcome in future approaches. Something in comparison with the FAO 56, maybe you know that Allen et al. Constructed stress values to reduce the water supply, and this is something we don't deliver in Geisenheim. However, under the conditions, under Central European conditions, we have no constraints for water, and we believe that vegetables are really poor in stress tolerance towards water. So maybe they are still not relevant. The pros of our approach, that this approach really considers environmental factors, which again affect the plant growth directly. And we believe that compared to rigid stage duration, as published by others, we feel that this phenological stage dependency fits better to the course of the crop ET than those rigid durations. And I think still it's a very, very simple approach and feasible to apply under field conditions, and it's technically very little susceptible to interferences. So maybe this is the reason we had a survey, and the farmers really gave the feedback that they need really simple approaches to be able to deal with. The second approach is the KC estimation via stage duration. Even if I already mentioned the cons of those approaches, we were interested in what's the deviation of those approaches compared to others under Central European conditions, because in context of automation and digitization of decision support systems, we would like to support farmers to really get rid of any manual aspects of their decision support systems. So this rigid stage duration approach might be very, very beneficial from the practical point of view. Also for a broader implication or implementation of our approach, we followed a project where we developed a free and open source software, so that we open our approach, we open our algorithms to everyone who would like to involve Geisenheim irrigation scheduling in sophisticated decision support systems, maybe comparing the scheduling also with the logistics of irrigation machine, whatever. So therefore, we went ahead and open up our approach. And this open source initiative was derived or realized by providing our source code to everyone who would like to do it. And therefore, we also followed the attempt to really get rid of any manual aspects. So therefore, we proved whether the attempt of Aaron et al. Also fits to vegetables and also fits to our climate conditions, where those KC values have a specific duration. I know this is not a very good figure, but maybe you can already see that we have a high fluctuation. And what I would like to show you here is for the example of lettuce, which is transplanted very often within a vegetation period, sometimes 20 times. You can see here the 3 different KC stages of lettuce. And the duration of those KC stages vary within a season, and vary also if it's planted in March, April, or in the following month. So due to this variability, maybe really due to the high fluctuation of our climate variables during the vegetation season. So if you just look on the red line, which reflects the mean temperature in a season, you can see that for sure plant growth interacts with those drivers, and therefore we believe that these rigid duration are not really the best attempt to schedule irrigation scheduling. Therefore, we think that the determination of phenological stages to account for the KC value is inevitable. So this is also something we observed and compared maybe to other regions where we have more constant climate variables, or rather semi-arid conditions, where we don't have the impact also for of precipitation. Maybe those rigid duration stages might fit better than under Central European conditions. So this is really the negative aspect, that we believe that mean values do not reflect the actual plant development and may therefore distort the calculation of the crop-specific water plan. However, for those who have to decide if they do any scheduling or not, maybe this may be even better than no irrigation scheduling or no balancing. And especially for those farmers who might miss to select the appropriate KC values as shown for the classical Geisenheim irrigation scheduling. The most promising attempt so far was derived from the approach of a specific temperature sum model for predicting the changes of KC values. And this is something I want to show you now. These approaches were followed within two projects. The first was the development of a mobile application of GS. So also here the focus on automation, digitization of our approach. I will show you immediately. And also a European Innovation Partnership project where we involved farmers and the feedback of those was implemented in the further development of this application. This mobile app is focused really to facilitate the application of Geisenheim Irrigation Scheduling, and it works not only field but also plot specific, and shows the irrigation demand also by the easy way of a traffic light system. So for every crop, for every plot, and also for every field, we have a visualization of irrigation demand and what might ease also the logistics of irrigation machines or sprinkler machines. And the basis for this also totally automatically system is this our approach. And this is quite specific and different to other temperature sum models because we do not estimate the Kc values itself, but the dynamics of the Kc values. And our models is based on Kc max and Kc min values, which are derived from the classical approach, and the parameters which are then crop specific are derived then to run the climate water balance. Another specificity of this approach is that the curve coefficients from this model are derived from the development of fresh matter. So you might ask, why did we parameterize with fresh matter? The simple reason is that, as you all know, that plants do not only act as we predict them to grow, and we observe that every model has to be adjusted to local conditions or to specific climate conditions, the prevailing conditions during the crop growth. So the easiest way for farmers to adjust their own model is just to weigh roughly one single plant, and based on the biomass, we can simply adjust the course or the slope of the curve. So this is the reason of our parameterization aspect. So I'll show you our advantages or our benefits of this approach for several crops relevant in Central European conditions. So lettuce is a classical transplanted crop. It's a hybrid, so it's very uniformly grown, and so we are very satisfied with the model obtained for lettuce growth. In the evaluation trial, so we run several irrigation trials by comparing the classical step model compared to this dynamic model, and we found that the model based on estimates reach the same level as the sophisticated model. So this was a very good result for us, and even the dynamic model had a higher use efficiency because of the significantly reduced water supply. So this works very well for lettuce, and also onion, a sown crop in open field, showed us a very good model fit for the changes of Kc by the biomass. And also here, the model, the new model is in no way inferior to the classical one, as you can see here. However, with this evaluation trial, we didn't reach a higher use efficiency. So the reason might be in the course of the ETC during the season, and therefore I would like to look closer to the ETC course during the season of this onion, and I would like to compare with you the both models and compare them with the actual evapotranspiration measured via EDCO. I'll show you the results from of 2018, and you see here this gray area is the confidence interval of the measured actual evapotranspiration of onion by means of eddy Co. Here you see this pink line is the moving average, and the red line is the step model of the classical KC, and here you see in blue the dynamic model of the temperature sum model based assumption. So what is clear to see is that at the KC1 stage, so at the stage of germination, our both estimates or our both models underestimate the actual evapotranspiration. Just to give you a short picture of the situation, maybe explain why, and maybe raise doubts if it's really relevant that those lines match each other. So as I already told you, our fields in Germany are mostly irrigated via sprinklers. So we have high evaporation during the first developmental stages in Europe. And maybe this might explain this deviation between our models. In the course of further plant growth, we see that both models, that the classical KC also, and especially the dynamic model, approaches to the estimation and till the very end of or till harvest, we see that we have really a good model fit in context of or compared to the measured ones. So in this year, we see by the root mean square error that the new dynamic model just overfitted or the classical slightly, which has to be proven also in future trials or with other crops if we can improve the quality of the dynamic model. This was the good side of our model, but I also want to show you the constraints and of our model, and I think these constraints evolve also for other approaches, as shown for spinach here. For spinach, it's also a sown crop. We have no good model fit. And we observe in specific crops that we have a high variability among single plants. So they don't act, even if it's a FH hybrid, they don't act like those. And we have a high interspecific competition among those plants. And if approaches like ours are based on single plant observation, this really hampers the model fits. So therefore, for spinach, we didn't find really a good model fits. And therefore, we are running a lot of trials with spinach because we feel that maybe this might be the most challenging vegetable crops for us in open field science. So we think the temperature sum model for predicting the changes of KC is very simple to apply in decision support systems to use the single KC approach. And potentially it shows a higher accuracy and offers the potential of higher irrigation efficiency compared to the classical approach. But it's limited, or the parameterization is limited to those crops with low interspecific variability. And I didn't show here, but we have also plants with indeterminate plant growth, like celery, for example, or some tomatoes. And those crop growth models really make it difficult to derive those curve parameters, like for example, inflection points. So we believe that it's a good approach, and so further parameters for other crops are required, as shown for onion and lettuce. For sure, to be complete, and even if I don't show you own data, I would like to emphasize the efficiency of the estimation of KC values via spectral reflectance. And maybe, as you know, often this was our interaction in concepts of Geisenheim irrigation scheduling. However, there are really good attempts for estimating KC values by vegetation indices, but you know better than me. And so this is something I would like to discuss with you. I know you did a lot of work in that field, and I see that you took a lot of field crops, and I would be very interested to discuss with you, according to your experiences, the potential, the requirements, and maybe the constraints for remote sensing approaches for estimating KC or irrigation requirements for vegetable crops, maybe also under European conditions. The reason why we focus rather on proximal sensing approaches than on remote sensing approaches is maybe clear due to the temperate climate and the involved clouds compared to your conditions. This is the most limiting aspect, really the quality of the pictures we obtain from the satellite imagery, but also the resolution. And as I mentioned before, we have really usually small-scale farmers and involving small fields, small plots for the several sets of vegetables in open fields. So even in our experimental site here in Geisenheim, we really suffer from the resolution. So therefore, we focus on site-specific observations, and these are derived from proximal sensing approaches. So I would like to show you our current approach in doing so. This is my PhD student who works with different sensors for the proximal sensing, and what we are focused on is really the leaf and plant-based observations. And we do not only observe single leaves, but also single dots on the leaf area. And so we use sensors which are commonly used in agriculture. For example, this is area sensor for site-specific and partial-specific fertilization, and therefore we also detect vegetation indices to derive information about water supply and also nitrogen supply. Just to give you an insight of our limitations, we observed from our proxy sensing approaches is, for example, very good shown by our spinach leaf. And if you see, if we account for the chlorophyll content and the reflectance which is related to that, we have a high variability, even within one leaf shade, and we have to consider not only different parts on a leaf shade or blade, we also have to consider for leaf thickness, and therefore we have to consider the position of the plant and therefore the age of the leaf on a plant. So there are a lot of crop-specific, plant-specific phenological aspects which have to be considered, and to overcome the constraints of uneven distribution of chloroplasts in the leaves, of the high variability with respect to leaf age, orientation to the sun, etc. We have to increase the sample size per leaves and combine measurements at a different scale, like leaf and plot scale. And we have to enhance our models at this time by adding factors of leaf age and developmental stages too. However, we believe that this small-scale monitoring at the first attempt reflects very well the plant status and the changes due to environmental conditions. And it delivers opportunity of direct reference measurements for vegetation entities evaluation. And luckily, those measurements are very undisturbed by the weather conditions prevailing in Germany. So this is something we are conducting in our future approach called geocensus, and there we combine the detection of nitrogen supply and also of water supply to combine the recommendations and the decision support systems. Maybe this might be for you already totally familiar in context of fertigation. If you irrigate on if you put fertilizer by means of drip irrigation, but as you told, drip irrigation is still very rare under Central European conditions. So we have to increase the water use efficiency and the nutrient use efficiency in open fields by combining the irrigation and the watering events. And therefore, this is something we do in this project, in the georeference sensor-based data management system for site-specific irrigation and fertilization of open field crops. So I think what I want to show you is what I raised before the requirements of the proximal sensing of to deliver the water status. We are also using artificial neural networks to involve all these plant parameters, all these crop and soil and climate parameters to derive very promising approaches to account for all these variabilities in the environment of our crops, especially for this crop spinach with this high intraspecific variability. So this is something we are dealing at this moment, and maybe we can have a discussion on that afterwards. Finally, I would like to give you a brief insight in our experiences we gained in our project in Namibia, where we established an irrigation technique where we developed an irrigation system for local conditions and also try to choose the appropriate crops, the appropriate irrigation scheduling, facing all these socioeconomics and also environmental conditions there. So the goal was to develop and optimize irrigation technologies for the use of treated wastewater in semi-arid regions. What we did, we used those ponds derived from water plants, and we took this water quality and tried to establish a irrigated field. So this was before and after our attempt to do so. We compared 3 different techniques. I'll roughly show you the difference of furrow irrigation and drip irrigation here. And what we use is this pond water, this treated wastewater, and the challenge was that we don't have really current electricity, so we had also to face the situation that sometimes we didn't have energy to run our pumps. So therefore, we established a storage tank just to have at every time of our irrigation events enough pressure to run our irrigation system. So what we did, we compared not only the irrigation systems, but also the irrigation scheduling based on the Geisenheim Irrigation Scheduling. So we took KC values of published data about from Solon, also from Lucerne. So we have full and reduced irrigated systems, and we compared different techniques. Actually, what we learned from this 3-year trial is that we believe that knowing the physiology of crops and their response to drought is as important as the designing of a proper irrigation system for agriculture in arid regions. And we learned that in situations where, in addition to water scarcity, the region faces prolonged droughts, drought-resistant plants like sorghum perform better than drought-tolerant plants. And maybe one has to really convince farmers to change the crop and to really put much more effort on those drought-resistant crops. We also learned that in order to design a proper irrigation system, in addition to the technical issues and the efficiency of the system, we must have a broader view of those socio-economic and economical conditions of the region, so that the system can be operated sustainably. And for example, we developed a drain system which performed very well in our experimental conditions, but farmers didn't have the material or they couldn't buy the material to run the system after we left the research site. So this is something we really have to consider in future. Maybe we need much more socioeconomic science also in those projects. So that's the perspective from the semi-arid area Namibia. And to finally conclude, in overall, we believe that under Central European conditions, considering the requirements of farmers, considering the climate, the soil, and also the variability of crops grown in Europe, we believe that the KC approach, if it's based on measurements of the ET, are provide a very good basis for crop-specific water balancing. And we observe that the estimate of KCs for the crop water balancing is the most widely used, and maybe due to its universal applicability, also due to universal applicable evapotranspiration or reference evapotranspiration. However, there is a trade-off in the scientifically and the technically feasible accuracy in water balancing, and there are error pronenesses and in the evaluation of measurements or by the farmer. So we can increase the sophisticated models, we can increase the requirements of farmers, but if the data gained by the farmers is not adequate, all those models fail. So therefore, we have always to consider this trade-off and the technical gains at farm level. So therefore, we believe that this evolution of approaches has to be continuously focused also in future, and we believe that if we interlace this with the technical process of, for example, Agriculture 5.1, we believe that in the near future we'll find approaches which are accurate in water demand, but also feasible for the practical implications. And finally, I just want to keep you in mind that the crop water balance is a formula with many terms and parameters. So the KC value is just one term in the product, and also you have to account for precipitation amount and irrigation amount, and especially in this temperate climate in Europe. We have to be aware that we have to record precisely those climate variables for the ETO measurement. We have to be aware that the ETO varies with the model, so you have to choose the appropriate reference evapotranspiration model. We have to account on a plot level the precipitation on site to account for the correct balancing. You have to record precisely the applied water quantities and for sure the appropriate KC values. And therefore, this is something from a holistic point of view which offers a lot of challenges in accuracy and also the trade-off between scientific and technical aspects. So, so this is my idea about the opportunities and constraints for the climate water balance. And now I'm open for questions. Thank you very much.
Thank you, Jana, for being right on time. Who would like to go with the first question?
Offer, can I do that?
Yeah, please, Victor, go ahead. This is Victor Al-Khanati from the Institute of Agricultural Engineering in Volcani.
Yeah, hello. Thank you very much for your excellent presentation, very informative for me. Although I'm in ag engineering, I do work with irrigation and remote sensing. I have two small questions. One is whether you have considered to use thermal data in addition or instead of the hyperspectral measurements. And the second one, specifically some of the results that you showed for the project in Namibia is that if I understood it correctly, you use the same amount of water irrigating by furrow irrigation and drip irrigation. Is that correct?
That's correct. So first to answer the last question, we attempted to compare 3 different techniques. So therefore, we applied the same amount of water. So that's true. We put the same amount, but on a different time scale. So for sure, the furrow irrigation obtained the whole volume for 1 week, while the drain or drip system obtained less volumes by the course of the week. And to answer your first question, yes, this is a really good approach, thermal imagery to account for in our systems. And yes, we do so. And we also did in Namibia to evaluate our approaches by means of changes of leaf temperature. Thank you very much for your question.
Okay, does anybody have another question?
Maybe if I'm allowed to ask a question to you, and I think this is my question I raised here to you. What's your experience and what are your ideas about remote sensing for vegetable crops under Israeli conditions, but maybe you have already some experiences for other climates?
I've only worked in Israel, but in Israel also vegetable plots are very small, like you mentioned, and then the satellite pixel footprint is a limitation. And I think going to proximal sensing, like you suggested, is very feasible. You can put sensors on moving platforms like the pivot irrigation system or a tractor or a UAV. And as you mentioned, at the leaf scale, it is probably more noisy and more difficult to estimate the KC, and then the canopy scale is probably a better approach. And well, in Israel, we have experience with field crops that grow in big fields where mostly because of the eddy covariance constraint, because of the eddy covariance footprint, which is also fairly large. And so we get more than one pixel inside that footprint. We worked on cotton and processing tomatoes mostly, but also we did some measurements in wheat, which is not irrigated in Israel, just to measure the water consumption. And this winter we're working on potatoes, and this is the first time we're in a system that is not drip irrigated, but sprinkled. And we also find it very noisy, especially early in the season because of the evaporation measured by the eddy covariance system that is not related to transpiration. So maybe the Geisenheim approach, where you weigh in weighing lysimeter, I noticed that you only had to adjust for the middle season and end of season KC values, but in the beginning of the season, it was pretty accurate. I imagine that this is because of the root development that doesn't happen in the weighing pot, but does happen in the field. So maybe a combined approach to calibrating the remotely sensed KC models or proximally sensed KC models, using those two approaches to measuring the actual water consumption would be good.
Yeah, good idea. Thanks, Afa. Yeah, and one further question in context of the eddy code: do you run your irrigation scheduling based on eddy code measurements in practice?
We haven't done so. We usually work in commercial conditions without interfering with the farmers' management. So we just pick good farmers that had good results and that get guidance from prominent field agronomists. And we hope that they are irrigating ideally or close to that. And we calibrate based on that, but we do several repetitions, at least 3 seasons per crop, and we try to account for the variability in our KC estimation models. We did have one irrigation experiment in processing tomatoes, but it was in smaller plots where we couldn't use the eddy covariance. And we used 2 different approaches to estimating the required irrigation. One was using a multispectral camera on a UAV. And the other approach was as a neural network that we trained based on a meteorological station and the eddy covariance on the other hand. So when we had the model to connect it to, we no longer needed the eddy covariance, and based on the meteorological station, we could estimate the tomato water consumption. And both methods on that trial gave almost the same irrigation recommendation, which was also the same as the control, which is the processing tomatoes in that farm were irrigated according to a different system completely, that also used the soil sensors as monitoring for the amount of irrigation applied. And so both are methods, one based on remote sensing and one based on a neural network, proved to be as good. And we plan to repeat that this summer to establish it.
And how does the irrigation technique impact your estimations? Like I showed you that in Germany, we mainly use sprinkler irrigation, so all the fields are wet, not only the rows of the plants. So how, what's your experience? Because you mentioned you also do sprinkler irrigation, but I assume that most of your systems are based on drip irrigation.
Yeah, that depends on the crop and the area, and the size of the field also. But yes, there's a heavy use of drip irrigation, and it's more efficient. And also, yes, I think for calibrating the model, maybe it's better to use the drip irrigation system, because later on, when you estimate KC from spectral data, you mostly rely on the vegetation and not the soil. or some mix of the signal, but that is dominated by the reflectance of the vegetation, especially once you're near full cover.
Yeah.
And so once you have a model, I think the irrigation system is of minor concern. Maybe you have to account for the irrigation system efficiency when you translate the estimated KC into an actual irrigation recommendation. And that probably also depends on the soil type that you have.
Yeah. Yeah, thanks, okay.
Yeah, Victor mentioned before the thermal camera. And now we were starting another experiment to maybe combine both methods. One to estimate KC from multispectral data and then combine that. So once you reach full canopy cover, right, and KC doesn't change too much anymore, you can still have some stress occurrences, and then you can adjust your irrigation according to thermal data, maybe. That's what we're looking into right now. Victor, you wanted to ask a question?
I would like to comment on the question that you asked here. I have a very rigid opinion about spectral data and the ability to sense water demand remotely. I agree completely with Ofer that until full cover, then spectral data can very efficiently define the cover and then have a good estimate of KC. But after full cover, the ability of spectral data to estimate water demand or water stress or water whatever else is, I think, more limited, or at least has a time delay with the actual stress development. First of all, in the water windows, water vapor atmospheric windows, we cannot sense actual water. What we can sense is in the different areas where water is, the effect of water deficiency is expressed indirectly by the differences in the leaf structure, which is too late. Maybe not too late, but after the water stress has some effect on the crop.
Yeah, I totally agree with you, Victor, about this issue, and this is something we're really heading at a current study, that the stress, the water stress, impacts the leaf size, the leaf structure, leaf mass area, and all this issue, which have again an impact on the signal which is detected remotely. So, and we have to detect the stress before we have those effects on the area or structure.
And on an additional point, I think you've done a great job with the app that you've built to manage irrigation. I've already downloaded it from the GitHub. I already told you. And I'm going to see how we can maybe use it or incorporate in some of the works that we do, or something. It's really very nice, and I really congratulate you for this activity. Very good.
Thank you very much, Victor. And I'm really open for a collaboration with you if you use it, and if you have questions. I would really, I think it would be very beneficial for our team too if someone uses this and gives us feedback. So thank you very much for your interest on that, and I think maybe we keep in touch in the context. Thanks.
Thank you.
Okay, so it's noon, but if someone has a last question, we can still squeeze that in. Okay, then if not, thank you very much, Jana. I appreciate you taking the time to speak to us, and yeah, also sorry for